Hey Wheaton North, Mrs. Trotta. On your last video for the gas unit, we're going to talk about ideal gas law calculations. We've got one more formula for you. Before I get into it though, just a reminder that an ideal gas that we can use this formula for is one that meets all of the ideas or rules of the kinetic molecular theory for gases. They have to travel in a straight line. None of their intermolecular attractions are engaged because they're going so fast. Their volume is negligible compared to the space that they take up, so the volume we're actually measuring is of their container, and their collisions are elastic, so they never slow down and become a liquid, so they stay a gas. We didn't talk in the last video about what a non-ideal gas is. There are quite a few times when a non-ideal gas could be. Well, I guess the one we did mention was when they start to condense, so right at the bottom of the slope for a heating curve. Another scenario that could create a non-ideal gas is when you have them under super high pressure. They're forced so close together that their volume becomes significant, and that would change the way they act a little bit. There's some other instances when a gas could be non-ideal as well, but we're going to worry about when they are following the rules. One last thing we need to get into is because changing the temperature and the pressure can affect the volume and the amount of gas and all that stuff, we do have an STP that we store gases at. So it's important, if your problem says that here's a gas sample at STP, that they are telling you that it is at a standard temperature, which is 0 degrees Celsius, which, as we know, we need to plug in as 273 degree K. And just for your, personal geekiness, it happens to be 32 degrees Fahrenheit if you wanted to know. The standard pressure, there are so many pressure units, so this might look overwhelming, but 1 atmosphere, that's like sea level, so it kind of makes sense, like we want to store it at sea level. The equivalent of 1 atmosphere of pressure is 14.5 psi. This is psi is pounds per square inch. That's used a lot in industry and manufacturing. kPa, kilopascals, is what we used in all of our labs. We use that a lot in chemistry. If you have a barometer that measures air pressure at home for weather, it's measured in millimeters of mercury, so it works a little bit like a thermometer, where the mercury levels go up and down, and a guy named Tor invented that. So those were 4 of the most common pressures. You'll probably see kPa or maybe even atmospheres in your problems that you'll have. So you'll pick one of those that you want to use. Alright, so ideal gas formula is PV equals nRT. So you'll recognize the P, the V, the N, and the T. What's new here is to make this equal sign work, we have to throw in a constant. It's not quite equal, so it was always off by a factor of, they decided to call it R. And because we have so many different units for pressure, we have different versions of R. If you are working in kilopascals, then you would use 8.314. And then this is the unit for R. So it's kind of a crazy unit, like the specific heat unit was a little weird. It includes all of our variables. But the important thing is that the pressure variable is kilopascals, and we have liters and Kelvin and moles. So what if we're not using kilopascals? Then we have a different R for if we're using atmospheres, and we have a different R if we're using torr or millimeters of mercury. Those are the ones that are usually used in chemistry class. So you'll notice that the rest of the units all stay the same, liters, Kelvin, and mole, and that will come into play in a little bit. Alright, when you're doing these problems, the pressure unit can be anything. The volume has to be in liters because it has to be able to cancel out. The temperature has to be in Kelvin, and moles has to be in moles. Alright, just like before, when you're solving a problem, always identify your variables. That will help you figure out which formula to use. Now that you have the combined law and the ideal, you need to know when to use the combined and when to use the ideal. There's no adjusting of the ideal gas law formula, so that part doesn't apply. That only applies to combined, and then of course we'll solve for the unknown. I have 2 problems for you. The first one is kind of a straight up problem, and then problem 2 kind of shows all the twists and tricks that we can add in to make it a little bit more challenging. Alright, so when you're reading this, you can see that the pressure is 202.6 kilopascals. The volume is what we're trying to solve for. The moles is, what is it? Oh, here it is, 0.050 moles, and the temperature is 400 K. So we only have one version of each of these, unlike the combined where we were given a second set of these numbers. So because we're only given one set, we know it's PV equals nRT. That means we need to know the R. We're working in kilopascals, so we're going to choose the 8.314 R value. Again, just like in combined, when you're plugging your numbers in, you've got your P, your V, your N, R, and T. Put them all down in the same order as the formula so I can find any mistakes that you're making and give you a little bit higher partial credit on the test. And then you would multiply and then divide by 2.2 or 202.6, and you get 0.821 liters when you solve for that. And that would be the volume of this sample of gas. We're not changing it, so we don't need a new one. This is just what it's at right now. All right, so for practice problem 2 with all of the twists, we have an unknown pressure. Our volume is 7,500 milliliters. Our moles, N, they give it to us in grams. We're going to have to convert that to moles. And then our temperature is 20 degrees Celsius. Again, we have only one of each of these, so we know we're using PV equals nRT, which means we have to pick an R. The R has to match the pressure. We're not given a pressure. We're not told in the problem what pressure in atmospheres, what pressure in kPa, so we're not limited by the problem. So we really could pick any R. I happen to pick the same one because I was copying and pasting from the last slide. But you could have picked a different one if you wanted, and your answer would have been whatever unit this is. All right, so I picked 8.314, and we need to plug these in. But before we can plug them in, you'll notice all of these things have to end up canceling. And milliliters and liters will not cancel. Grams and moles will not cancel. Degrees Celsius and Kelvin will not cancel. So this is worst case scenario where we're going to have to convert every single one of these into the right unit. Thank goodness you've already learned how to do all of these things. Don't worry, I'll remind you. All right, so to convert milliliters to liters, this is just a metric slide, the decimal over 3 places, so that's 7.5 liters. Remember, you have that chart in the front of the room to look at. Converting grams to moles. Do you remember how to do this? All right, direct proportion is your friend. So you need to figure out how many moles are in 20.16 grams of hydrogen. Set this equal to what you know. The relationship for 1 mole of H2 is 2 grams. And you figure this out, you take your H. Each H weighs 1 gram. We have 2 of them. So 1 mole of hydrogen gas will weigh 2 grams. Well, but if I had 20 grams instead, how many moles would that be? Cross multiply, solve for X, and you get 10.08 moles of hydrogen gas in your 20 gram sample. All right, last one, converting Celsius to Kelvin. You should know how to do this. You just learned it. You add 273 and you get your Kelvin, 293 Kelvin. All right, now we've converted everything so our units all match. Now we can finally plug it in. We have P, V, N, R, T. Remember, put it in order. Then do your math. Multiply these 3 together, divide by 7.5, and you get 3,274 kilopascals. An easy problem for you and a hard problem, and now you guys are off to do your own worksheet. Good luck.